Hello dear students, welcome to Ekeeda. Today we are going to start the topic of shear force and bending moment diagram. We will take some questions on shear force and bending moment diagram. Mainly gate questions will be there, but apart from gate, I have chosen some other questions also, and the good questions, so that the shear force and bending moment diagram concept may be clear, right? So we will do some questions, mainly gate questions. Before that, we will have a brief idea of shear force and bending moment diagram. You have to go through the thorough theory lectures before that, so that you maybe know that how to solve the questions of shear force and bending moment diagram, some formulas or some concept, right? Brief idea I will give here also, but mainly I will discuss the questions of gate exam, right? So let us start today's session. Yes. So before I start the today's topic, shear force and bending moment diagram, let us have a brief idea before we start this question. Let us have a idea. We are not talking about this question now. Just we are taking the idea of what is shear force and bending moment diagram. What is shear force? What is shear force in a beam? We are talking about in a beam, right? So in a beam, how to find out the shear force? You have to go through the theory lectures. I hope that you have gone through the theory lectures, and then you will be able to find out the what is the shear force at a cross section of the beam. Suppose we have a cantilever beam now. This is A, B, C, D. A, B, C, D. This is a cantilever beam. Cantilever beam. So this is a cantilever beam, and there are some forces: 800 Newton, then 500 Newton, and 300 Newton, right? Before that, before this start this question, let us formulate or define what is shear force. So if I want to find out the shear force at certain section, suppose X section, this section, suppose at this section I want to find out the shear force. So mathematically, shear force is the algebraic sum of, this is the algebraic sum of all the forces, all the forces to the left. Either you should take left side of the beam, this section. I have taken this section, X section is taken. Either you should take algebraic sum of all the forces to the left or to the right of the section, to the right of the section, right of the section, right? So whatever forces are there, you have to take sum of all the forces, right? To the either to the left or to the right of the section, right? So you have to take these forces you have to consider while finding the shear force, right? Now some forces are in downward direction to the right of the section. If I take right of the section, there are two forces. How many forces are there? There are two forces. One is 500 Newton and another is 800 Newton. Two forces are there, isn't it? So if I have to take the algebraic sum of these two forces to the right of the section, this is our section, X is our section, and I have to take the algebraic sum of these two forces. So I have to see whether these forces are downward or upward. So these forces are to the downward of the section, right? So I have to take the sign convention, whether I have to take the downward forces to be positive or negative, right? So we have to take the sign convention of our own, right? So it is your choice what sign convention you choose. So for shear force, there is a general trend. However, it is not final. You can take your own sign convention also, but this is a general trend that If there is a shear, there are forces. This is like two forces are there, 500 Newton, 800 Newton. If these are downward in right direction, because to the right of this section, the forces are in downward direction. These are downward, right? To the downward directions are there, then it is taken positive. And or to the left of the section, if it is upward, again this is taken as positive. So this is the sign convention for positive shear force. To the right of the section, it should be in downward, then it is positive, or to the left of the section, if it is upward, then it is positive shear force. Similarly, we can take the negative shear force as negative shear force as opposite of that. If it is to the right of the section and it is upward, this is, I have chosen sign convention. You can choose your own sign convention also. So if it is upward to the right of the section, then it is taken as negative, or it is downward to the left of the section, again it is taken as negative. So these are the sign convention which we will follow in this lecture, or in my theory lectures we will use these sign conventions, right? So algebraic sum of all the forces to the left of the section or to the right of the section, right? This is the shear force. So here, if I want to find out the shear force at x point, fx, x section, then what are the forces? This is one force is 800 Newton. 800 Newton force is there. So for 800 Newton force is downward to the right of the section. So it is positive. So I will write 800. And to the right of the section, there is another force 500 Newton, right? Another force is 500 Newton. So this 500 Newton is again downward. You can see here, this sign convention will be used. Again downward to the right of the section, again it is positive. So I will write plus 500. So shear force at x section will be 1300 Newton, right? So Fx in this case is 1300 Newton. This is the example. This is only an example. We will solve this question completely, but for the time being, I am writing the one part of this question for summing up the theory part, right? So quickly, you should know that shear force, what is shear force at a x section? So shear force at any section, we have taken x section here, is the algebraic sum of all the forces to the right of the section or to the left of the section. We have taken to the right of the section, right? If we would have chosen the left section, then there will be reaction at this point, and we have to find out first the reaction. So in cantilever beam, it is always preferable to find out the shear force taking the free end. This is the free end. Free end into consider, we have to consider the free end, right? Because in free end, you have to know to find out the reaction. Otherwise, you have to find out first the reaction, and then you have to find out the shear force, because shear force is reaction is also taken as the external force, right? So first you have to find out the RA if you want to take the left of the section, right? And we are not finding RA here, right? So this is the uh, shear force to the uh, at a section X, right? Isn't it? So now, what is bending moment then? This is the shear force. Now we have to take the bending moment. Bending moment. What is bending moment? Suppose I take a section again. I choose a section. I'm deleting some part of this. Yes. Suppose I take again a section, any section. I'm changing the section now. Suppose this section I am taking, this section, right? This is the section at a distance x, from the free end. This I have chosen now, right? Any section you can choose, but I have chosen for simplicity only one section, x section. Suppose at this x section I want to find out the bending moment. So what is bending moment? Theoretically, how it is defined? So bending moment is the algebraic sum of it is the algebraic sum of all the movements, all the movements of the forces to the left or to the right of the section. Means now you have to sum up all the movement of the forces, right? Either you have to take the left of the section or you have to take the right of the section. So now in this case, in this example, what will be the bending moment? And first again we have to find out the we have to assign the sign convention. What is the sign convention? So bending moment are two types, sagging and hogging. So when the bending moment is in this way, that it is leftward anticlockwise, clockwise, or rightward anticlockwise, then this is taken as positive in our sign convention. We have chosen this sign convention. You can choose your own, right? For the time being, I have chosen this sign convention, right? To the left of the section upward, and this is positive, and to the right of the section anticlockwise, it is again positive, right? Or there is a vice versa also, that negative bending moment we have chosen as the leftward if it is anticlockwise, or rightward it is clockwise, then it is taken as negative bending moment, right? So this is the sign convention we have chosen for bending moment, right? So sagging and hogging bending moment, we have chosen one as positive and one as negative, right? So this is the bending moment. Now at this X section, what is then bending moment? What is then bending moment? We can choose any part, right or left of the section. So we can choose for ease the right of the section. Otherwise, we have to take the reaction here at A point, right? So it is better to choose the free end where there is no reaction required in case of cantilever, particularly in case of cantilever. So to the right of the section, there is only one force, 800 Newton. So bending moment at X point at section will be equal to 800, the moment of 800 about X. So it is, the distance is X. So this is 800 multiplied by X. And then you have to see whether it is, because it is rightward, so with the, whether it is clockwise or anti-clockwise. It is clockwise. You can see here, this 800 will make a clockwise bending moment, right? 800x, right? 800x. So it is a clockwise to the right of the section, and clockwise to the right of the section is taken as negative, right? This is similar to this, negative. So this is negative, minus 800x. So this is how we find out the shear force and bending moment at a section, right? Now we have to draw the shear force and bending moment diagram. Using these equations, we can now draw the shear force and bending moment diagram. So let us start with this question, how to draw the shear force and bending moment diagram, right? We have to draw the shear force and bending moment diagram, right? I'm clearing this, and further we can start with. So So let us take this section, this as an example for the time being, right? This is not GATE question, but it is a good question. A cantilever beam of length 2 meter. It has a length of 2 meter. You can see here 0.5 meter, 0.7 meter, and 0.8 meter, right? So total length is the 2 meter. And some point loads are there, 800 Newton, 500 Newton, and 300 Newton. We have to draw the shear force and bending moment diagram for the cantilever beam. For this beam, we have to draw the shear force and bending moment diagram. how to draw the shear force diagram and bending moment diagram, right? So let us draw the shear force and bending moment diagram, right? Now the shear force is changing from D to C. There is only one force is there. If I take the right of the section, because cantilever being free end is always good to take the free end, right? So to the right of the section, if I take section here, to the right of section there is only one force, 800 Newton, right? So it will be valid between D to C, because between D to C there is no other force. So first I have to divide into three parts. First I have to take the section between D and C. Then I will take the second part. I will take one section here also, right, between B to C, and that will be valid for B to C, right? Then section between C to B, when I am going from C to B, and then I will take the section third part, which will be valid from B to A, because the load is changing as I am moving from D to A, right? So for the third part I will take the section between B to A, right? So this question will be done in three parts basically, right? For first part D to C, then load is changing, that's why I am changing the section C to B, and then again load is changing and I will take the section between B and A, and this is how this question will be solved. Now we can solve this question now. So let us now take a section between D to C, right? And I'm going to find out the shear force, right? So I am taking the section between D to C. Here I am taking a section at a distance x, from the free end, right? So what will be the Fx? F at x, sum of all the forces to the right of the section. So there is only one force, 800 Newton, and this is uniform, and this Fx will be valid. This Fx will be valid between D to C. This will be valid for D to C, right? Because I have taken the section between D to C and there is no other force between D to C. So this is valid for D to C. So F at D will be 800 and F at C will be again 800, right? Now I can draw the shear force diagram for this. Now shear force diagram can be drawn. So let us draw now shear force diagram. So this is our baseline on which shear force diagram will be drawn. This is A, B, C, and D, right? A, B, C, D, right? At D point, the load is 800. So I am taking 800 here. This is suppose 800, around 800 Newton up to this point. This distance is equivalent to 800 Newton, right? This force is 800 Newton, and it is constant from D to C. D to C it is constant, right? Because there is no other force, right? So this is constant from D to C. So I will take a straight line here like this, right? And here also the load is 800 Newton, right? At this point the shear force is again 800 Newton, right? So this is how the shear force is drawn from D to C, because this is 800 Newton, Fx is valid between D to C, right? So this is how we draw the shear force between D to C. For one thing I have done, right? Now, but I have to find out the shear force between C to B also and B to A also. So I will take a section. I will take a section between C to B. So let us take a section here, any point X between B to C. Say I am taking from the free end. The distance I am taking is from the free end, and again I am taking X. New X is there, right? Let us forget about the previous X. Now it is new X, right? You can say X1. I am taking X only, right? This is new X. So now we are taking again Fx between C to B. Now I have taken the section between C to B. It will be valid for C to B. What is the shear force? Sum of all the forces to the right of the section. Sum of all the forces to the right of the section. To the right of the section, there are two forces, 500 Newton and 800 Newton. So this plus this, right? And these are positive according to our sign convention. According to our sign convention, It is positive because our sign convention says that this is positive shear force if I am taking rightward downward and leftward upward. This is shear positive shear force. And contrary to that, this is negative shear force, which is rightward upward and leftward downward. This sign convention we have chosen. You can choose any sign convention. So again, to the right of the section there are two forces, 500 and 800, both are positive. So 500 plus 800. So this is 1300 Newton. And again, this is constant. There is no x term. It means this is a constant. So at C point, the shear force is 1300 Newton. And at B point, again, this is 1300 Newton. So there is a jump at C point. At C point, previously it was 800, now it is 1300. Previously it was 800, now it is 1300. There is a jump at C point, right? So at C point, we can draw the shear force at 800 to, there is a jump to 300, means 500 is added up. And then it is constant, then this is constant throughout the B to C, right? Up to this point, right? So this point is the shear force of 1300 Newton. So at C point, there is a jump from 800 Newton to 1300 Newton. And this point also, the shear force is 1300 Newton. And this is constant between C to B. Between C to B, it is constant. Right? Now, third section, B to A. B to A. How to find out B to A? The shear force between B to A, let us take a section X between B to A. So now I can choose a section. Now I can choose a section between B to A. So let us take a section between B to A. Let us take from the free end. I am taking from the free end only. This, right? This I am taking from the free end. So from free end, I am taking a section between B to A, and I have to find out the Fx, which is valid between B to A. So this will be equal to algebraic sum of all the forces to the right of the section. Algebraic sum of all the forces to the right of the section, right? This is our concept. Yeah. And how many forces are there to the right of the section? There are three forces now. 300 Newton, 500 Newton and 800 Newton. Three forces are there, and all three are positive. To the right of the section, they are downward. So all three are positive according to our sign convention, right? So this is 300 Newton plus 500 Newton plus 800 Newton. So this will be 1600 Newton. So this is the 1600 Newton force, and because there is no x term, so this is again constant between B to A. This is again constant, right? So at B point, the force will be 1600 Newton, and at A point, again the force will be 1600 Newton. So at B point, the force is 1500 Newton, 1600 Newton. So this is the line of 1600. This point is of 1600. Okay? This point is of 1600 Newton. 1300 plus 300. 300 is added up, and this will remain constant for the rest of the section between B to A. And this point is again the point of 1600 Newton. And you close up the diagram, meet this point, right? This is 1600 distance. This is equal to 1600 Newton distance, right? And this is positive throughout the section, right? So this is the shear force. So this is the shear force for the entire beam, right? From D to C, it is constant 800 Newton. From C to B, it is constant 1300 Newton. From B to A, it is constant again 1600 Newton, right? And this is the shear force diagram for this cantilever beam, right? Now we have to find out the bending moment diagram. Bending moment diagram for this beam, right? So for bending moment diagram, let us take section again. As we previously taken the section, again we have to take the section, right? So let me clear this. I will draw the shear bending moment here only. At A point I am extending here, at B point here, this B point, here it is C point, C point is extending, and extension of D point, and somewhere here I will draw the, on this line I will draw the bending moment diagram, right? On this line, this horizontal line, I will draw the bending moment diagram, right? This is A, B, C and D. On this plane, on this line, I will draw the bending moment diagram. Again, I have to take the section between D to C, then between C to B, and then between B to A. So let us take the section between D to C. Let us take this section X at a distance X from the free end. So let us take the section between D to C at a distance X from the free end, right? So what is bending moment? First, the sign convention. Sign convention for bending moment. What was the sign convention for bending moment? For sign convention, you know that for sign convention we have taken this sign convention positive clockwise on left section, anti-clockwise on right section. This is positive bending moment, and this we have taken the negative. This sign convention is chosen by us only. You can choose any sign convention, that is not an issue, right? This is the negative bending moment, right? So this was the sign convention. We will follow this sign convention. So because we are taking to the right of the section, and right of the section the forces are downward, it will make a clockwise movement, right? Clockwise movement will be there, so it will be negative, right? So at X point we have taken mx, m at X point, and it is valid between D to C. D to C. It is valid between D to C, right? So this will be equal to moment of algebraic sum of all the moments to the right of the section. We are not taking to the left of the section, because to the left of the section we have to take the reaction at the fixed end of the cantilever beam. So it is easy in case of cantilever beam to choose the free end, right? So we are choosing the free end, right? That's why we are taking it to the right of the section. So to the right of the section there is only one force, 800 Newton. Only 800 Newton force is there. So moment of 800 about X is 800 into X. 800 multiplied by X. Only one force is there. Moment of this 800 is 800X. But according to sign convention, this is clockwise. Clockwise to the right of the section. This so this is this part, this sign convention, right? It is negative. So we are taking negative, minus 800X. Now it is variation, right? So if it is linear variation, then what is the bending moment at D point? X is 0. So bending moment is 0. And at C point, what is the bending moment? The bending moment is X value is 0.8. 0.8. There was some connectivity issue. So we were drawing the bending moment. So bending moment at this section we have already drawn the shear force. Now we are drawing the bending moment. So bending moment we are drawing at this section, right? Bending moment was we were drawing, right? So at this plane we want to draw the bending moment, right? Here, here we want to draw the bending moment A, B, C, and D, right? Here we are going to draw the bending moment. So how to draw the bending moment? First we have chosen the sign convention. Sign convention was, this is positive, clockwise to the left of the section, positive bending moment, clockwise to the left, and anti-clockwise to the right. This is positive bending moment. And negative bending moment, this is negative bending moment, anti-clockwise to the left and clockwise to the right. This is negative bending moment, right? So we have to draw now the bending moment diagram. So we will take a section between D to C. We are taking a section between D to C. Section between D to C. X section we have taken, and this at X section, what is the bending moment? And that bending moment will be valid between D to C, because there is no other force between D to C. So we are taking Mx between D to C, that will be equal to moment of 800. Only one force is there, 800 Newton. So this is 800x, and it is negative. 800 is making a clockwise bending moment, right, at X point. So this is minus 800x, right? And it is variable because X term is there. So because X term is there, X will be varying. So bending moment will be varying, right? It will be increasing in negative direction, isn't it? So at D point, the value of X is 0. At D point, the value of X is 0. So MD will be 0. Put X is equal to 0 here. At C point, the bending moment is the distance is X is equal to 0.8 meter. X is equal to 0.8 meter. So put here minus 800 multiplied by 0.8. So this will be minus 640 Newton meter. Minus 640 Newton meter, right? Minus 640 Newton meter is there. Means from 0 to minus 640 Newton meter variation is there from D to C with a linear variation. This is a linear variation, right? So somewhere here at C, in the C point, somewhere here, suppose this point is the moment of bending moment of 640 Newton meter. And at this point, D point, this is 0. From 0 to 640, it is varying linearly in negative direction. So this is the bending moment diagram between C to D or D to C, right? This is the one part of this question, that the linear variation is there because X term is there. If this is X term, then it is a linear variation. And at endpoints, C point and D point, it is valid between C to D or D to C. At D point, it is 0. At C point, this is 640 negative. So in negative direction, lower direction is our negative direction. So this is our negative direction. In negative direction, right? It is basically minus 640 Newton, right? So this is the bending moment at point C, right? So next part of this question, that we have to take between C to B. Now we will take the section between C to B, right? So let us take the section between C to B, which is valid between C to B. So I have taken a section this at a distance X from the free end. At a distance X from the free end, I have chosen this section, right? So if it is X from the free end, what is the bending moment at this point, capital X? What is the bending moment? So at X point, again, which is valid between C to B. So this is Mx between C to B, right? Now we are taking between C to B, right? So what are the forces? And X is taken from the free end. X is taken from the free end, right? And it is valid between C to B. So what are the forces? Moment of all the forces, algebraic sum of moment of all the forces to the right of the section. And to the right of the section, there are two forces, 500 Newton and 800 Newton. We have to take the moment of 500 Newton and 800 Newton. Two forces are there. You can see here, 500 Newton and 800 Newton. So first take the moment of 800 Newton. This is minus, because it is according to sign convention, it is clockwise couple is there, right? So this is minus 800 multiplied by x, right? Minus moment of 500 multiplied by the distance c to x, this distance, c to x distance, this distance. This, what is this distance? C to x, this distance. This distance is x minus 0.8. X minus 0.8. This distance is x minus 0.8. Isn't it? Isn't it? X minus 0.8, this distance. So x minus 0.8. Okay. So again, this is minus 800x minus 500x and plus this will become 400, right? So this will be minus 1300x plus 400. So this is the bending moment mx, which is valid between C to D, right? So this is the bending moment, and it is again the linear variation. There is a linear variation again. You can see here, x term is there, x term is there, and this x term making the linear variation. So this is a linear variation, right? If it is x square, then it would be a parabolic variation. Now it is a linear variation. Now at B point and C point, what is the bending moment? So at B point where x, value of x is, what is the value of x is 0.8. So this will be equal to, put here 0.8, so minus 1300 multiplied by 0.8 plus 400. So this will come out to be, I am writing directly the value, B point minus 1550. So minus 1550 Newton meter. You can calculate it using the calculator, and it is the bending moment at point B. And what is another point? Another point is C point. So what is bending moment at C point? C point, and at C point, no, B point is 1.5 meter. We have written here something wrong. At B point, the value of x is 1.5 meter. So there is slight change is there, that the B point is a point of x is equal to 1.5. Yeah? You can see here 0.7 plus 0.8. This is 1.5. So at B point, the value of x is 1.5 meter. So put here 1.5 meter, right? Instead of this 0.8. And at C point, the value of x is 0.8 meter at C point. So at C point, what is the value of bending moment? That is minus 1300 multiplied by 0.8 plus 400. So this will come out to be again minus 640, which came earlier, minus 640 Newton meter. So there is no abrupt change in bending moment. There is no change in bending moment at point C. You can see here. It means that the point load is not causing any change in bending moment at certain point, instant change, right? There is no abrupt change, right? Because this force is acting through this point only. This force is acting through this point only. So at this point, this is the bending moment. Excuse me. At this point, the bending moment is changing from 640 to 1550. This is 1550, suppose. This is 1550 Newton meter. So here it is changed from 640 to 1550, and it is linear variation. You can see here x term is there. It means this is a linear variation, right? So this is a linear variation. right? It may not be a straight line. It may not be a straight line. Like it is not a continuous line from B to C or C to D. There may be a slight slope, maybe there, change, maybe there, slope change may be there. I can I can choose another point here so that you see that the slope is different. This is 1550 Newton meter, and there is change in slope. Straight line, but the slope is different. Two lines have different slopes. So C to B have different slope, and D to C has different slope. So this is the bending moment between C to B, and again it is negative, right? Negative bending moment. Now the third part. Now we have to take the section between B to A. Third part, B to A. So let us take the section between B to A and draw the bending moment diagram. So take the section. Say here I have taken the section at a distance x from the free end. I am taking the section from the free end only, and this is a section x. So what is bending moment at section x? So this is mx, and it will be valid between B to A. So this will be equal to, now there are three forces. Algebraic sum of all the forces to the right of the section, right? So there are three forces, 300, 500 and 800. So the moment of 800 into x, moment of 500, that is 500 multiplied by x minus 0.8, right? This distance is this distance, moment of 500, this distance. So this distance is x minus 0.8. 0.8 is removed here, right? So this is x minus 0.8. And then the moment of 300. So this is minus 300 x minus 1.5. This distance. Moment of 300 x minus 1.5. It is x minus 1.5, right? So this is how the bending moment is obtained. Now we can find out the bending moment at point B and A. So at B, put the value of x as 1.5. X will be 1.5. And because this is a point load, there is not a moment at B point, this is a point load. So previous bending moment will be achieved. If you put here the value of 1.5 in this equation, which I am making in rectangle, in this equation, if you put the value of x as 1.5, you will get the value same as the previous value, that is minus 1550. This is minus 1550 Newton meter. And at a point, the value of x will be 2 meters. So this, put here 2 meters in this equation, right? And you will get the value of MA, and MA will come out to be, when you put the value of 2 meters, the MA will come out to be 2350. So this is minus 2350. You can put the value and get the answer, right? Use calculator. And this is a linear variation. This is a linear variation because x term is there, right? X term means y is equal to mx plus c. Linear variation. If x square term is there, this is parabolic variation. If there is no x term, it means a straight line, no variation, right? But there is a variation and linear variation from 1550 to 2350. So this variation is from 1550 to 2350. Suppose this is point of 2350 Newton meter. And this is a straight line, make a straight line out of it, right? So this is how the bending moment diagram is obtained, right? So this is the bending moment diagram for this cantilever beam, right? So this is how we can obtain the bending moment diagram, right? So 0 to 640 Newton meter, negative direction, then 640 to 1550 Newton meter, a straight line, again straight line and different straight line, the slope may be different, and then 1550 to 2350, again there is a straight line but different straight line, right? So D to C, C to B, and then B to A. So this is the shear force and bending moment diagram for this cantilever E. let us take this question. In this question, a beam of negligible mass is hinged at support P and has a roller support Q. So there is a hinge joint at P point and there is a roller joint at Q point, right? So two supports are there at P point. This was asked in GATE 2020, right? This year only. Right? So at P point there is support, at Q point there is a support. A point load of 1200 Newton. A load of 1200 Newton is applied at the center, right? 5 meter from the hinge joint at point R. This point is R. R point is there. The magnitude of the reaction force at support Q is, what is the magnitude of reaction force at point Q, which is a roller joint, right? This we have to find out. So before that, you should go through the theory lectures, that how many types of supports are there, how many types of supports are there. So before that, I will little explain the types of supports basically, right? So you should know the types of supports. And what are the reactions on these supports, right? So one type of support is hinge joint. Supports or joint, you can say joint also. The name is joint also. Hinge joint. Hinge joint, like in our doors, our almiras, hinge joint is there, right? So how it is shown? This is how the hinge joint is shown. This is a hinge joint, right? So it will allow the movement. You can rotate this beam about this hinge joint. If this is A joint, you can rotate this beam about A joint, but it is not allowing the horizontal movement of this beam, and it is also not allowing the vertical movement of this beam, right? So because there is some reactionary force acting from bottom side, which is causing the A point to not to move from A to A in vertical direction. And also there is a horizontal force, horizontal reaction. This is RH, horizontal reaction, and this is vertical reaction. So there are two reactions are there, right? So this is horizontal reaction and vertical reaction are there. RV I am writing vertical reaction, RH is the horizontal reaction, and it is not allowing the movement of this point, A point, in neither in horizontal direction nor in vertical direction, but you can rotate, right? So it is not resisting the movement. It is not resisting the movement. It is just resisting the horizontal and vertical forces, right? That's why the reaction developed here, RV and RH. So two reaction will be developed at a hinge joint, right? Vertical reaction and horizontal reaction. So two reaction will be developed at a hinge joint. Then another type of joint is the roller joint. Roller joint. Roller joint is like you have coolers in your home, and it has wheels on the bottom, right? You can move horizontally, but you cannot move vertically because the earth is producing the reaction. You cannot move vertically, but you can move it horizontally because rollers are there, right? So roller joint is like this. This is a roller joint like this, and this is a beam, right? So it is not causing the horizontal reaction, neither it is causing the movement, reactionary movement. It is causing only the vertical reaction, because it is allowing only the it is allowing to move in clockwise or anti-clockwise direction or horizontal direction. We can move it in horizontal direction. That's why there is no horizontal reaction, only vertical reaction is there. So only one reaction is there, because it is allowing the movement of in horizontal direction, and the rotation can be done, right, about this whole roller joint, right? So this is the roller joint. And in hinge joint, two reactions are there, right? And third type of support or joint is the fixed joint. fixed joint. Like in a wall, you put a beam inside the wall like this, right? This is a fixed joint, right? In this case, it is not allowing the rotation of the body, not allowing the rotation, neither it is allowing the horizontal movement of the beam, nor it is allowing the vertical movement of the beam. It means there is a vertical reaction, horizontal reaction, as well as the clockwise or anti-clockwise movement reaction is there, right? So reactionary movement is there, horizontal reaction is there, and vertical reaction is there. So three reactions are there. Three reactions are there, right? In this case, right? So resisting moment is there, resisting horizontal force or horizontal reaction is there, resisting vertical reaction is there in this fixed joint, right? In cantilever beam, we have a fixed joint, right? So this is a three types of joints which will be used in our shear force and bending moment diagram chapter, right? So let us come to this question. Let us solve this question now. So one is the roller joint, and now roller joint is like this. Roller joint is like this now, right? So if it is like this, then only in vertical in this direction, now it will become horizontal, reaction will be there, right? At Q point, the reaction will be at this point, Q point, right? Like in previous case, it was vertical, now it became horizontal, right? Perpendicular to the rollers, perpendicular to the rollers, right? So this reaction is there. So one reaction will be there in this direction, horizontal direction, perpendicular to the rollers like this, because it can move now in vertical direction, Q point. We are talking about Q point. So this is the reaction produced at point Q, because roller joint produces only one reaction. So this is the reaction at Q point. And at P point, there will be two reactions. This is R vertical and this is R horizontal. Two reactions will be there at P point, vertical and horizontal reaction. Vertical and horizontal reaction, right? So two reactions at P point will be there. So at P point, two reactions are there, and Q point, only one reaction is there in this way, horizontal reaction, right? Now it becomes horizontal because our beam becomes vertical, right? So the moment at P point will be zero because the body is in static equilibrium, right? So for static equilibrium, the condition is that, what is the condition of static equilibrium? You should know that, right? Condition of static equilibrium. Condition of static equilibrium. That the sum of all moments about certain point should be equal to 0. Sum of all vertical forces should be equal to 0, and sum of all horizontal forces should be equal to 0. Then only then we can say that the body is in static equilibrium. So we are talking about this body. That body is in static equilibrium, right? So at any point the moment will be 0. So at P point we can choose the hinge joint. It is always good to choose the hinge joint or roller joint, right? So we are choosing the hinge joint. So the moment at hinge joint will be 0. So sum of all the moments at P point, which is the hinge joint, should be equal to 0. So how many forces are there? One is RH, another is RV, and one is 1200, another is RQ. These are the forces, right? So RH, RV, 1200 and RQ. Four forces are there. But the RH is passing through P point only. So moment of RH about P, about P will be equal to 0 because this P point is passing through this point only, right? That's why the moment of RH is 0. Moment of RV about P is again 0 because RV is also passing through P point. Moment of 1200 about P will be equal to 1200 multiplied the distance. So if you take the clockwise moment as positive, so it will be positive. So 1200 multiplied by 5. So this will be 6000 Newton meter. and moment of RQ about P will be equal to, it is anti-clockwise about P, right? You can see here this RQ is making an anti-clockwise. So this is, you can take minus RQ multiplied by the distance, vertical distance. This is 4 meters, 4 meters, 4. So this is minus 4 RQ, this much Newton meter. And sum of all these forces should be equal to 0. So this is 0 because sum of the moments at P point is 0, MP is 0. So it means all these moments should be equal to 0. Sum of all these forces. So 0, sum of all these moments plus 6,000 minus 4 RQ should be equal to 0. So from here we can find out the RQ, the value of the reaction, that will be equal to 1500 newtons. So this is the answer of this question. So this is the answer of this question, that the reaction at point Q is RQ, which is 1500 Newton. Let us take one more question. Which question? Yeah, this question is also good. So this question was asked in 2017. 2017, this question was asked. For a loaded cantilever beam, of uniform cross-section, the bending moment in Newton millimeter, the bending moment is given in Newton millimeter, that is mx equal to 5x square plus 10x, and x is given in millimeter, right? Measured from the free end, it is measured. The magnitude of shear force in the cross section at x is equal to 10 millimeter is, what is the value of shear force, right? This is asked in GATE 2017. So we have a cantilever beam. Like this. This is a cantilever beam, and there are some forces. We don't know what are the forces. There may be some forces like this. There may be some UDL like this. We are not clear about the forces. It is not given to us and not required, right? And at certain distance x, from the free end, it is given that the bending moment at this point, the bending moment at x, mx, is given as 5x squared plus 10x, right? They are asking that what is the magnitude of shear force in the cross section at x equal to 10 millimeter. When the x is 10 millimeter, what is the value of shear force? We have to find out F shear force at when the x is 10 millimeter. This we have to find out, right? Now, from the theory lectures, you should know that the shear force is the differential of bending moment only, dm by dx. F is equal to dm by dx. You should know that, right? You have to go to theory lectures. It is explained there that a shear force is equal to dm by dx, right? So from here we can find out the shear force as a function of x will be equal to dm by dx, which is equal to the differentiation of m, which is equal to 5x squared plus 10x, and that will be equal to 10x plus 10, right? So this is the shear force as a function of x, right? But we have to find out the shear force when x is equal to 10 millimeter, and the x is already given in this equation 10 in millimeter. So we have to not to change the sign convention or dimensions. X we have to directly put the 10 mm because the in this equation the x is given in millimeter. So this is 10 multiplied by 10 plus 10. So this will come out to be 100 newtons. So answer of this question is F is equal to 110 newtons, the shear force at a distance x from the free end. So this is the answer of this question. So these are some of the questions which are asked in GATE exam. about the shear force and bending moment diagram. This is a very easy question. There are always one question about the shear force diagram. Sometimes in few GATE exams, I have seen that this is a common data question also there, right? Four marks question are there, right? In first part, we have to find out something. In second part, you have to find out shear force or bending moment, right? And based on that, you can also find out the bending stresses and shear stresses, right? That we will do in the next lectures, coming lectures. So if you don't know how to find out the shear force, you cannot find out the shear stress. And if you don't know how to find out the bending moment, you cannot find the bending stresses, because the failure take place due to stresses, either due to shear stress or bending stress. So that, for that, you should know the how to find out the shear force and bending moment at a section. And the most important thing is to find out the maximum bending moment, because most of the failures in beam take place due to the at a section where the bending moment is maximum, because the bending stress is maximum there, right? So although shear stresses are very small compared to bending stresses, most of the failures take place due to bending stresses, but we should know how to find out the shear stresses also, right? So let us meet on the same day, Saturday at same time, 8 p.m. Next week we will meet now in the coming week. Coming Saturday we will meet now, right? Okay. So take care. Good night.